for our judges. This is paper 449 CQ. Ready?
Yes.
Rolling call.
Yes.
All right. Hi everyone, my name is Akshita. I'm from the University of Florida, and today I'll be talking about my work on microscopic study of hydrogen sulfide transport in zeolitic imidazolate frameworks, or ZIFs. So as I'm sure you're all aware, H2S plagues a lot of our industrial operations ranging from wastewater treatment to natural gas processing. And given the toxic and corrosive nature, there's a lot of push to develop new materials that can help isolate and separate H2S. And so recently, there's been a significant amount of research devoted to using metal-organic frameworks or MOFs in such separations. And so obviously having a good understanding of transverse properties of hydrogen sulfide inside these materials becomes really important. So my research is devoted to studying microscopic diffusion inside these materials. And why do we want to study microscopic diffusion? Well, there are a lot of interactions between sorbates and sorbents that dictate such separations, and these details are often lost in larger macroscopic transport studies. And I use a technique known as pulse field gradient NMR for my work, and I combine high magnetic fields and large field gradients for this. And these are both really important, especially for this work, because the high magnetic field allows me to look at really low concentrations of hydrogen sulfide. And the large field gradients allows me to probe displacements on the order of hundreds of nanometers and tens of micrometers, which is often the size of these particles. So I can actually tell you what's happening inside the particles rather than just what's happening on one side of the membrane and coming out the other. And the novelty of this work lies in the fact that this is the first microscopic diffusion study of hydrogen sulfide, and the total concentrations that we're operating under are between 180 ppm to 6%. So this is the first time, as I said, this work has been done, and so it comes with its fair share of challenges. So we're looking at H2S absorbed in ZIF-8 for this study, and we're using proton NMR. And this is unconventional already because you don't usually use proton NMR with high magnetic field for diffusion studies in porous materials because you get something like what's shown up there in red. It's a really broad peak. You can't figure out what's what in that. And the reason for that is a lot of anisotropy effects. But now if I apply a PFG sequence, specifically the 13 interval sequence, I eliminate a lot of those effects and I get a nice narrow peak. And if I can manipulate this sequence, I see it evolving, and this tells me that this is probably a true peak, and I can assign this as H2S. And so PFG sequence is already a really powerful way of identifying H2S signal even at low concentrations as low as 180 ppm. But as promised, I want to actually measure diffusion of H2S. And to do this, I need to observe attenuation or decrease of signal with gradient strength. And I need to observe this for various diffusion times. So I know, first thing you'll hear and you tell me, okay, these spectra don't look great. There's a lot of signal to noise ratio loss that's happening, and that's mostly because of the low concentrations. And this is challenging, but we're working on looking at higher concentration samples as well. But even then, you can see that at 20 milliseconds and 40 milliseconds, there is a decrease in signal between the largest and smallest gradients. But to get an estimate of diffusivity, I need to see consistent attenuation over gradient strength. And so at 60 milliseconds, you do see that there is a consistent attenuation. And from this, I can estimate that diffusivity of H2S inside ZIF-8 is less than 3 times 10 to the negative 13 meters squared per second. And this is slow. And just to give you a context of how slow it is, simulation work shows the diffusivity of carbon dioxide and methane, also relevant industrial gases, is 1,000 times larger. So now we can use this property exploited for separation purposes. So just to give you a bigger picture, yes, I've already shown you PFG NMR can be used for studying microscopic diffusion. However, I can also use it to track changes in terms of the properties of these materials after exposure to H2S, because H2S is corrosive. We don't know how stable these materials will be over weeks or even months and years. And so I can use PFG NMR to do that. And this, in collaboration with people from Georgia Tech and University of Wisconsin, we can really pool together our information and our research and develop a thorough understanding of hydrogen sulfide diffusion in ZIFs and also how it affects their structural and absorption properties. And this is really important because, yes, there are a lot theoretical studies and a lot of computational studies trying to predict what will be a great material, but when it really comes down to implementing these materials in industry, I believe it's experimental data like this that can draw the bridge from lab to industry. And with that, thank you for your attention. This work is done with, in conjunction with the Energy Frontier Research Center at Georgia Tech.
Okay, excellent. Now I'm going to repeat for anyone who hasn't been